It's been a really great workshop. I've had a lot of fun and learned a lot of interesting things. I realize that I'm the last speaker, so I'm standing between you and your taxis to the airport, which maybe you don't want to take, but also lunch. So I'll try to keep things as simple as possible. I'm also going to assume that you paid perfect attention in the previous talks, and so I don't need to introduce anything that I'm going to talk about. I'll do a little bit, but not too much. Okay. And this title is kind of vague. So what I'm going to talk about is essentially how complex are quantum states of quantum field theories and quantum gravity, and how we can represent those quantum states in an interesting way by thinking about the structure of entanglement in those states, and how maybe we can use this to either do new kinds of classical simulations of quantum physics, or very maybe how we can use early quantum devices to help us do a little bit more than we can do now classically and solve an interesting problem. Okay, so I'm going to talk about a lot of different work, which I'm going to kind of overview, but the main new idea at the end is work in progress with Isaac Kim at IBM, and I'll indicate that when it comes up. Okay. So here's one way to think about some of the influence that quantum information science has been having on my interest, which is quantum many-body physics. I started life in doing electron physics and got into other areas, which is to think in terms of problems that are easy or hard to simulate using all of our available resources, both classical and quantum. And so one impact that quantum information has had is it's inspired new classical methods, which I'll talk a lot about, tensor network methods, for example, which have let us push the boundary of what's easy by thinking about the way entanglement is structured in quantum states, quantum ground states, for example. And we've solved a lot of interesting problems, especially in one dimension. For one-dimensional systems, this has made an enormous amount of progress under the guise of DMRG, matrix product states, and so forth. But maybe there's still some interesting problem that we'd like to solve, perhaps in 2 dimensions, that's out of reach. So we're sort of made progress, but we're not quite there yet. And now another direction is to really do quantum simulation. I've made this kind of transparent because we don't really have quantum devices yet that are capable of doing things we can't do on the classical computer. But there's, of course, a lot you can do with such a device, and that's going to be a very interesting and rapidly developing field. So what I want to explore in this talk a little bit is I'm going to explain to you some of the things that go into this blue arrow. But I'm also going to present an idea for how we might be able to take this large blue arrow and add a small red arrow, add a small near-term quantum device to help us get to where we want to be, to solve some interesting problem as represented by this purple blob. And I hope that will become clear what I mean later in the talk, but for now, that's where I'm going. So this is the kind of question that I'd like to answer in terms of complexity. How many and of what quality of quantum resources do I need to simulate, say, an interesting quantum field theory? It doesn't have to be QCD. Of course, that's a very interesting quantum field theory. It could be a quantum field theory that describes a strongly interacting scale invariant critical point that you can realize in some material physics. Now, an even more ambitious question is, what is the quantity and quality of quantum resources needed to simulate an interesting example of quantum gravity? And actually here I'm presuming this is even possible. Maybe it's not. Maybe quantum gravity is a completely different computational class. But at least in one case, in the case of ADS-CFT, we think that's not true. And I think thinking in terms of the near term, this is echoing something that Andrew said in his talk, clearly the most favorable answer to these questions are we're going to utilize as much as we can about our existing understanding of the classical, how to think about entanglement and quantum information in these states. So we want to use as much information as we can, as much classical pre-computing to do as much of the work as possible. And so this is kind of the idea that I'm going to talk about at the end, how we can use a little bit of extra quantum resources to help our classical algorithm. So what am I going to simulate, and how will I do it? Well, there's lots of interesting things you could try to simulate. Dynamics is, of course, very interesting. However, even equilibrium physics in the presence of, say, fermions or other kinds of complex fields, for example, at finite density, this is already challenging for a variety of methods. Okay. For example, the fermionic Hubbard model is still an unsolved problem. Although we have a good sense of what the physics is from a variety of methods, and we're converging towards a complete picture, we're not there yet. And the approach I want to advocate is to think about tensor networks, which I'll explain what those are in a second. And these are really networks or ways of thinking about the quantum state that take advantage of the entanglement structure. And then I want to think about using these networks to represent the quantum state and then contracting them in the jargon to calculate physical observables. And that contraction can either be done classically. I just put the tensors on my computer and do some linear algebra, or maybe using a smallish quantum device. We might call this quantum-assisted classical simulation. Okay, so here's a tensor network. It's a bunch of blobs connected by lines. This is a sculpture by Alexander Calder, which I like a lot. So I want to show you how to use this kind of structure to solve interesting problems. So here's the model I'm going to take, the simplified model. I want to think about it one dimension. In fact, I want to think about it many dimensions, but I want to draw pictures for one dimension because that's the easiest. Okay. And I'll indicate where the dimensionality matters or not. So let me think about a spin chain, by which I mean a collection, a one-dimensional collection of finite-dimensional Hilbert spaces. That's these little black lines. So I have L of these things. And each of the black lines is a Hilbert space of some dimension chi, which is often called the bond dimension. And you should think of this physically as what I've done is I've taken some microscopic qubits, some microscopic spin-and-a-half degrees of freedom, and I've bunched them together into a big group. Okay. So this is some kind of coarse graining, which lets me talk in a convenient way about this system. Okay, so I'll call these things supersites sometimes because they're just, maybe I have some detailed structure at the micro scale, but I'm going to just group them together into some simple objects that I can work with. And as I drew here, you can think of these lines as being composed of, say, lots of qubit lines, curly L of them. Okay. And so this represents a quantum state of these L supersites. And if I want to do physics, I want to understand the physics of whatever system this is representing, then I need to be able to calculate properties, physical properties of this quantum state. And what I'll do that is to use the tensor network. And I'll use a particular tensor network, which is called the multi-scale entanglement renormalization ansatz tensor network. So let me just take a few minutes to explain what this means. So here at the top are again are my physical degrees of freedom, up here. And these blue boxes with 2 inputs and 2 outputs are unitary transformations. So I'm just rearranging the entanglement, the local structure of these physical degrees of freedom. And the object, you can see there's a kind of layered structure where I have one layer, then some simple states, then another layer, and some simple states, and so forth. And the way this works is I start with sort of the microscopic state. I try to do some operation which in effect disentangles some of the degrees of freedom, half the degrees of freedom, say. Which means I can place half every other line into a simple state, a 0 state. And then I have half as many degrees of freedom left coming down in some non-trivial quantum state. And I want to do the same thing again. Okay. So I want to do more operations that can somehow tease out an additional set of degrees of freedom. And I can keep repeating this procedure until I run out of things to disentangle. Or if the system is in thermodynamic limit, if it's infinite in size, then I can go on forever. And I'll caution you, not all these layers have to be the same. I made them all the same blue box, but in principle, the layers could be different, the different unitaries could be different. So this is a pretty flexible framework. However, one thing which is nice about it is that it has a scale invariant hierarchical structure. So it's like a renormalization group inspired tensor network. And so what I'm going to try to convince you by going through several different examples is that this kind of network we've learned in the last few years is as quite general structure and can represent a huge variety of different and interesting and phases of matter that we'd like to understand the physics of. And I'll emphasize too that there are generalizations to higher dimensions, but they're hard to draw. I'll show you one nice picture a little bit later, but that's the basic structure. So I want to talk about some examples now, and I want to talk about it in terms of some characteristic length scales. So the first is the lattice spacing. That's just how far apart these little sites are. Then there's a correlation length, C, which is how long range the correlations are. There's also what I'll call the entanglement range, which is how entangled the system is in some sense. These are often the same, but not always. And then I'll talk about this supersite size L, how it scales. So
yeah, that's what I was wondering. How do you, where's the change between correlation and entanglement?
Yeah, I'll give you an example in just a second. Okay. So let's start in the simplest thing, which is what are called trivial gap states. So here, trivial does not mean uninteresting. It just means that from the point of view of this entanglement measure, they're not that complicated. And so examples of trivial states are states that, for example, are insulating band insulators like diamond, mean field superconductors. These are states where there's an energy gap to all excitations, at least to electronic excitations. The correlation length is short, it's of order of the lattice constant. And we have strong reason to believe these states are lightly entangled. And what that means physically is that there is, you can imagine an experiment where you can sort of adjust the laws of nature at will. You can change the Hamiltonian of diamond. And you can find a path in Hamiltonian space, a family of Hamiltonians, labeled by this parameter little s, such that the Hamiltonian at 0 has a trivial ground state. Maybe it's all product state. It's all the electrons in little orbitals, like hydrogen atoms a centimeter apart. Or H of 1 is the ground state of diamond. Okay. And then because this is a gapped Hamiltonian, because it goes from a trivial state to the interesting state that we want to think about in time of order 1, you can use an adiabatic preparation to simply prepare this ground state. And then you go to Andrew's talk, and Andrew tells you how to turn this into a quantum circuit very efficiently, and you get out one of these circuits. And in this case, there's sort of no low energy field theory because everything's happening at the lattice scale. And so this is what the circuit looks like. I actually don't need a bunch of layers, I just need one layer, which is this adiabatic layer. And in this case, the supersite size is just going to be roughly the correlation length, because I just need to do, the correlation length may be the inverse gap. That's how long I need to run for to do this adiabatic optimization, so that's how many sites I need to coarse grain. Okay? So now there's another interesting class of quantum states called topological gap states. And here, these are much richer because now, although the correlation length is still small, it's still of order the lattice spacing. In some sense, the entanglement length is large. That is, these are highly entangled states, although they don't have any local correlations. So examples of these states are quantum Hall states. So these are states that are realized by electrons in two-dimensional semiconductor heterostructure where you apply a strong perpendicular magnetic field. They exhibit quantized conductivity and a lot of other really exciting physical properties. And we understand that these states are highly entangled in a certain sense, in a sense that I'll make precise in a moment. Another more speculative, or not more speculative, but not physically realized yet, example would be discrete gauge theories of the toric code, various kinds of surface codes. And then there are other examples called spin liquids that are conjectured to exist in certain quantum magnets realized in nature, but that's still a sort of open question. And here the physics is a bit different. Here the physics is that I can't go from the interesting ground state to a product state in one step. That's not possible. What I can do is I can double or halve the size in one step. So there's again this path in Hamiltonian space such that the ground state of H of 0 is size L and the ground state of H of 1 is size 2L. So in other words, you can think about having a system of L by L, putting some extra degrees of freedom in there, and adiabatically interpolating them, sort of interleaving them into the physical system of interest to expand it by a factor of 2. So this is the kind of scale invariance. And it turns out in these cases, the low energy field theory does make sense. It is interesting now, and it's a topological field theory. So for example, Chern-Simons field theory describes some of the physics of these quantum Hall states. And so you can kind of guess, based on the fact that you can go from L to 2L with this adiabatic path, that what the network will now look like is like this. You need all the layers, and all the layers are the same. Because every layer I go from, say, 4 qubits to 8 qubits to 16 qubits. So I'm doubling the size every time, but each of those doubling operations I can do with a constant depth quantum circuit. Okay. However, as I showed here, the supersite size depends on the correlation length. So if the correlation length gets long, then this methodology is going to break. So I'm not saying there's not a circuit, but this way of constructing it, where I use this gap path in Hamiltonian space, is not an efficient way of doing that construction. Okay, so far I've talked about trivial gap states. I've talked about topological gap states. I've argued that they can all be put into this framework. What about states that are gapless? That's always very challenging. So what about states where the correlation length is diverging, so is the entanglement length. So there's degrees of freedom at all length scales. So examples of this would be various kinds of non-interacting fermion systems. So metals with a Fermi surface or Dirac points. The things that Yuto talked about in his talk. Quantum critical points that occur in many materials are this type, some of them. And again, we don't have quite the same level of control as in the gapped case. But we understand on physical grounds that there should be some sense of scale invariance. So that size L and size 2L should be, quote unquote, in the same phase. And what that should mean physically is that they're related by a finite depth quantum circuit. And as Yuto showed in his talk, in the case of, for example, free fermions, we can use wavelet technology to actually explicitly construct such a circuit. And we have some other constructions that I'll mention, but this is sort of more of a conjecture, which we can verify in some cases, but we believe it's true on physical grounds. And in this case, now the low energy field theory, which describes the long wavelength physics, can be a conformal field theory. It can also be a scale invariant field theory, which is not Lorentz invariant. So we've heard almost nothing about that in this conference, but that's another interesting kind of quantum field theory. It doesn't have Lorentz invariance, but can still be strongly interacting and still be interesting to try to simulate. Okay, and that can be easily realized in these lattice systems. And again, this is what the network looks like, because it has a scale invariant structure. So I can't go from the physical state to a product state in one step. That's impossible. That's not scale invariant. But I can increase or decrease the size by a fixed factor with a constant depth circuit. So that's, again, what's happening here. So I'm able to sort of shrink, go from 16 to 8 here with this circuit, and then I can apply many of those to keep shrinking until I have, say, nothing left or just one spin left.
So it's like an adiabatic shrinking.
That's exactly right, yeah. It's as if I put the system in an expanding universe and I just blow it up very slowly. And what we can show essentially is if you design the dynamics of that expanding universe right, then you can get with high fidelity the correct quantum state. Okay, I'll also mention one last example, which is really interesting, I think, which are what I call holographic states. So here we now imagine something very, very different, very non-condensed mattery. Most of the previous examples I gave are sort of condensed mattery examples. They exist in the lab. But we could imagine with some cold atomic gas setup, like for example what Benny talked about, that we could eventually construct a collection of atoms, ions, photons, etc., that realize, say, a lattice regulated version of n equals 4 super Yang-Mills. As far as we can tell, there's no in principle obstruction to that thing. Now it's very complicated. So this is sort of a pie in the sky example. But nevertheless, it seems possible. And if you could do that, we have good reason to believe that this kind of quantum circuit that I showed here can still capture the physics. And in particular, there's a very interesting piece of physics where now we interpret this, here I sort of just drew this circuit, and I just said this is a way to represent the quantum state. It has this hierarchical, what's the physical interpretation of this? I sort of have degrees of freedom here, and I have degrees of freedom peppered all throughout this sort of higher dimensional curved geometry. What is the meaning of that? Well, in this holographic states, there is a candidate meaning. And so again, this is the network. You maybe see a pattern here. I just need to use the same thing over and over again. In these holographic states, we have an interpretation of the network in terms of some kind of geometry. So you see now I've sort of coarse-grained the structure a little bit. I've just simplified things. I've dropped all these zeros. This is a very coarse characterization of that network that I showed you on the previous slide. And you can see, if you sort of stare at this network for a little while, you realize it has a hyperbolic character, which means that if you look at the distance this way, it's, say, some number of sites, but as you go down in layer, the distance gets smaller by a factor of 2 every time, right? So it has this exponentially growing or shrinking character, which is characteristic of hyperbolic space. And so what you can show in this network is that, suppose you wanted to calculate the entanglement entropy of some collection of spins up here with the rest of the world. That's something you might want to do. Well, in this network, what you'll find is that that entanglement entropy is bounded in an interesting way by a minimal curve which cuts through this geometry in the interior. Okay.
When you say emergent, sorry to, is it okay to ask?
Of course, yeah.
When you say emergent geometry, are you also talking about space-time?
This is more like space,
Okay.
but maybe has space-time in it. That's sort of an open question, actually. And so this formula where you say that the entropy is like a minimal curve in some geometry, that's very reminiscent of a formula in ADS-CFT called the Ryu-Takenagi formula, which says that if I want to calculate the entropy of some region on the boundary, I should look in the bulk, I should find the minimal curve, and I should calculate the area of that curve. Right? So somehow this tensor network picture is actually reproducing at least crude level the physics of the Ryu-Takenagi formula in ADS-CFT, in quantum gravity. And it's not hard to convince yourself in some sense that this network geometry is like a coarse version of the spatial part of anti-de Sitter space. For example, you can look at the eigenvalues of the Laplacian on this graph, and they are the same as the low-lying eigenvalues of this thing. Okay. So to go back to the soup can analogy, which we heard about in previous talks, if this is the outside of the soup can, and the soup can comes out of the board, so I've shown you a slice through the soup can at fixed time, then here's where my sort of boundary degrees of freedom live. In here is the bulk, where the gravity lives. And what I'm saying is maybe we can interpret this bulk extra-dimensional geometry as being literally a picture, sort of a coarse-grained picture of this tensor network which encodes the entanglement. Okay. So that's one way in which you can make a connection between entanglement, between tensor networks, from the boundary point of view, and this bulk gravity. You can sort of see the bulk emerge, and it's built out of entanglement in some way. And to make contact with Daniel's talk, understanding of error correction has given us a better sense of why this has to be true and what kinds of networks you would need to have, what sort of properties they have to have in order for this to be true. Okay, but so the takeaway is that this kind of network, even if this ADS-CFT interpretation is not quite right, seems at a coarse level to capture the physics of even very strongly interacting, very complicated quantum many-body systems that are really complicated quantum gauge theories. Okay. Yeah?
If gauge imbalance is fundamental, don't you need to incorporate it in this area as well? I mean, local gauge imbalance.
Yeah, so that's a great question. I have two answers. One is it may not be fundamental. Like I can always add some matter degrees of freedom that essentially relax the gauge constraint, but are just very heavy. Alternatively, there are actually ways in this network to implement the gauge constraints. So that can be done as well. But that's a very important thing which we would have to think about carefully before we could really talk about doing, say ADS-CFT in this context. Okay.
So you're in a position to actually test alias CFG
That's right.
through these systems?
That's right. Okay, so what did we do? I tried to convince you that this tensor network framework is very, very general. So I talked about superconductors, I talked about insulators, I talked about critical points, I talked about holographic systems, and I tried to argue that these may all fall in this class. Okay. So what? Why do you care? I mean, it's a nice picture, but does it bias anything? So now let's try to calculate some physical property using our tensor network. So we want to take the tensor network state here, you know, the corresponding bra, and then calculate some expectation value of a physical observable. That's a standard thing. So here's the picture again, and let's suppose that I'm interested in this observable that, say, is supported on these two sites. For example, the Hamiltonian is typically a sum of local terms, and so one piece of the Hamiltonian would be an operator that I might act on two of these sites with. So how can I do that calculation using this network? Suppose I promise you that this network describes accurately the ground state. How can you use it to calculate something? Well, what you want to do is contract the network, or in essence, isolate the state of these two spins, and somehow use that to your advantage. And so here's how you can do it. This network is nice because it has very interesting causal properties. The way that information is piped through the network is very restricted. And so, for example, all these tensors up here, all these unitaries, they don't affect the state of these spins, right? Because they're sort of cut off from it. They're happening somewhere else. I can just draw a line like this and forget about them. So I can actually remove all of those tensors if I only care about the state of these two spins. Now similarly, now that I'm sort of a little deeper down, I can also remove these three, these two here, because again, it does not affect the state. Now I have some zeros that are just going up to the future. They're totally unentangled with the physical system. I can remove them as well. I can also remove these lower down gates. And I've simplified dramatically the tensor network, right? Because of this special hierarchical structure that it had, because of the way information is piped through this system. And in fact, these qubits, although they interact with, actually they're supersites really, although they interact with this thing in some way in the past, they don't actually interact later, so I can throw them away. I don't need the information contained in those degrees of freedom. And so now if you look at this thing a little bit, what you'll see is that although the original tensor network involved an exponentially growing number of degrees of freedom at every step, the actual state of these two spins only ever depends on a constant number of qubits. So for example, I start down here with 4. I do some entangling operations, I produce some state. Then I attach in 4 new qubits. Let's see, one got lost somewhere. Okay, it's not quite uniform, but I attach in some new qubits in some fresh, simple state, a 0 state. I perform some additional operations. However, some of those qubits can then be discarded at the end of the day. And I do the same thing again. I attach in some new qubits, I do some transformations, but again, some more qubits can be discarded. And so the general picture is that I can take order 1 supersites, depends on the details of this network and which layer you're at, but say 10 supersites. I can, at every layer, tensor in some fresh degrees of freedom. I can apply unitary transformation and then throw some degrees of freedom away, such that the number of degrees of freedom I'm keeping are always fixed. And I just need to do this a certain number of times. If the system has size L, then I need to do it for log L times in the worst case, because that's how long it would take to shrink L down to 1 with this exponentially shrinking operation. And so I simply need to take order 1 supersites and apply this essentially open system dynamics, where I tensor in some extra degrees of freedom, apply unitary transformation, and throw some things away. I need to do that a certain number of times. So this is why this network is very nice, because you could think about doing this on a classical computer. I don't need to keep track of all this extensive number of qubits. I can keep track of a small number of qubits, or supersites. And I can imagine just representing physically these unitaries as matrices on my computer and carrying this calculation out. So what I've really done is I've reduced the complexity of simulating, this n-qubit system to the problem of simulating a few qubit system, provided this special structure of the network is true. But as I tried to convince you, that's a good belief in many cases. So what's the good news? What's the bad news? So the bad news is, so far it seems that outside of one dimension, the classical contraction is not really doable, at least not for the bond dimensions we need to see interesting physics. For example, with a two-dimensional version of this Mera circuit with a certain local architecture, the computational cost could scale something like the 16th power of the bond dimension. So it's polynomial. So in principle, I've exhibited a polynomial algorithm to solve this problem, but the polynomial is so high that I just can't quite get to the bond dimension I need to actually solve the problem. Maybe I can tell you based on some estimate that I need bond dimension of 100 to calculate my physical property of interest. Maybe that's enough to accurately represent the quantum state. But, okay, 100 to the 16 is too large. Although maybe if our friends in Lattice QCD will give us their petascale machines once they're done with them, maybe we can do something. I don't know how they feel about that. So for example, you need to diagonalize a big matrix to calculate, you need to diagonalize a superoperator that does the transformation at every step. But it's a really, really big matrix. And you can't even put it in memory on your computer. Or at least it's hard, because it's not obviously sparse, for example. So I won't say that it's impossible to make progress classically. I'm sure that there are lots of tricks you can do. I'm not an expert in classical computation. It'll be really interesting to try to push these things. But it does seem like we're maybe hitting a bit of a wall here. So we had this wonderful success where we realized all these different kinds of phases of matter can be represented in this one framework. This one data structure captures so much. But it's just out of reach to actually use as a computational tool. But the really good news, I think, is that this is a classical simulation method which, if you like, ages gracefully in the era of quantum computational devices, right? It's a simulation method that if you had even a small or medium-sized quantum device, you might be able to use it to do something more than you could do classically. So, for example, if I could actually physically instantiate this open system dynamics, this qubits, tensoring in new qubits, unitaries, throwing them away, and repeating, if I could actually instantiate that physically, then the calculation might be feasible. Because now, instead of having chi, which is a big chi by chi matrix I have to store in my computer, now I just need log chi qubits to represent this. And as long as the unitaries that I need to do can be implemented efficiently in that qubit basis, well, then I might be able to actually do the calculation. So that's an idea that Isaac Kim and I have been pursuing, which I think will hopefully appear soon. So let me make some comments about that. So this idea says essentially that the state of order 1 supersites, say you want to calculate this quantum state of three neighboring sites. Acting like this works even if they're separated in space. So you can calculate correlations as a function of distance, can be obtained by acting on, again, order 1 supersites with order log L quantum channels. And this could describe the dynamics of the system even in a thermodynamic limit, or in a very large system size. The memory, there's no scaling with system size in the memory. That's determined by how big the bond dimension needs to be. That's, say, some fixed number for a fixed error, for a fixed local error. And the time, in principle, only scales logarithmically with the system size. And in fact, there may be even a fixed point of this dynamics so that actually I can essentially do thermodynamic limit without ever needing to look at infinite number of spins. So the key question then becomes, how big does this bond dimension need to be, and how complex are the unitaries when phrased in this sort of circuit language? So the comment, too, is that there's actually no strong dependence on dimension. So this whole procedure can work in 2 dimensions as well, or in 3 dimensions. The main difference is in the local architecture. So here, for example, is a Hamiltonian that John McGreevy and Shenglong Xu and I came up with. which has an exactly known interesting ground state. This ground state has scale invariant correlation, so it's a kind of quantum critical point, but it's not a conformal field theory, so it's not Lorentz invariant, even at low energies. But you can write down the exact wave function of this thing, and we showed in this paper that you can construct a Mera circuit in 2 dimensions, which accurately approximates the quantum state. And this is what the Mera looks like. So this system is defined on this honeycomb lattice. And you can see this 2 layers again, where I apply various transformations. These green things are unitaries. These are controls. So there's a complicated local unitaries. There's some other complicated unitaries here, and then these blobs are the unentangled degrees of freedom. So I'm doing what I did before, where I do some local operations and then produce zeros plus extra lines that come out. For some reason, that this is drawn going the other way as before, but just rotate your head by 180 degrees. But you can kind of see where the complexity comes from. There's just a lot of little pieces, a lot of moving parts. If each of these is chi, and I want to put an operator here and calculate an expectation value, it's just going to it's going to have to involve a lot of different little legs, and it's just going to get complicated because of the complicated. But from the point of view of, and in this case, we could estimate that you needed a bond emission, say, of 60 or something like that to maybe accurately, to guarantee that you could get accurate physical approximation to this quantum state. Okay, but 60 is still too high, at least for my laptop. Again, maybe if you really push classical computing, you can do something, but at this stage it seems difficult. So comment 3, and this is really, really important, is that the gates need not be ideal. So this would be crucial. If you want to do anything on a near-term device, you're not going to be guaranteed that you have ideal gates and qubits that are safe. And I think, so we did some simulations, which we'll report on in the paper, but I think there's 2 physical ways of thinking about this. So one goes back to this expanding universe picture, and in that picture, if you have some finite density of errors, and you insert in fresh, cool degrees of freedom, then the energy gets diluted out. So you're not sort of making a mistake that builds up in time. Now, more mathematically, from the point of view of this calculation, where I'm applying a quantum channel many times, that open system dynamics can be stable to small changes in the parameters, provided the system has some kind of gap in the spectrum, in the spectrum of this open system dynamics. In other words, the long time behavior is normally very unstable. You know, if you make a small change, you can go off to a very different place. But if the system is sufficiently dissipative, if it sort of moves its information away in a nice way, well then actually the long time limit can be stable. So the fixed point may not change very much. And so actually you could imagine that physical properties could be computed even with noisy gates. And actually there's a physical reason why there's a gap in these systems. If, for example, the system is a conformal field theory at low energy, then we know that the spectrum of this superoperator is related to the spectrum of scaling dimensions. And those have a gap in their spectrum. You know, they don't start at 0, they have some finite size. And so actually we know physically that there should be a gap in this superoperator. And therefore we can expect physically that it should be stable to small perturbations. Now, exactly how small and exactly how stable is of course an important question which we don't really know the answer to. It seems that they're stable but not super stable, so this is something I can't be more quantitative about at this point. And so the final question is, how many gates do I need to implement in this qubit perspective? Well, the answer is I need to do not that many. So in all these examples I showed you, there's some dependence on the error, which is usually polylogarithmic in the error, which is quite good. And then some dependence on the physics in some other way, so a correlation length or some local data about the field theory. And this dependence is there, but it doesn't seem too bad. So it actually seems like a rather small depth circuit. So for example, in the free fermion example that Yuto gave, a depth 8 circuit is already enough, acting on say 8 qubits, to get sort of 10 to the minus 2 or 10 to the minus 3 accuracy in your exponents. The accuracy tends to decay exponentially with depth, with increasing depth. So it seems, you know, I don't want to make a precise statement, but it seems like favorable scaling. And in fact, even in the holographic states, we can use recent conjectures relating complexity and geometry to give an argument that the complexity, even in that case, even in the strongly interacting theory, is probably not that large. Maybe it goes like central charge, which is not that high. Okay. So the conjectures of this kind of structure, this like low depth circuit, giving a good approximation to the physics is a general picture. And so what should we actually aim to do? I think in principle, we could look at a non-integrable spin chain or say some interesting model in 2 dimensions that's hard to solve, like the quantum Ising model or some frustrated spin model, and try to actually implement this. These models are nice because they have a relatively simple local structure, so the number of qubits you may need is probably not that great at first. Maybe 30 qubits, maybe 50 qubits that are not too noisy could actually be enough to do a version of this supersite open system construction. And then you could imagine something like the following. You simply minimize the energy variationally using your device. Got it. You can actually calculate the energy. The energy is one of these local observables. So you minimize by hand the tensors. I mean, you change the tensors by hand to minimize the energy. And you construct this network. And then you can simply calculate or really measure physical properties. And if you have a nice way of implementing translation invariance, this energy minimization may not even depend on system size very strongly. Now, if you have to do every single tensor, then that's bad. Or not bad, but it takes more time. But if you have some way of enforcing translation invariance approximately, then you can do better. But of course, it's not a free lunch. There's all the usual potential problems with variational approaches. We can get stuck in minima and so on and so forth. Another idea would be you could actually try to implement a known circuit, but which can't be addressed classically because it's too complicated. So for example, this hexagon model I showed you in 2 dimensions is of this type. We actually wrote down what the tensors should be, but we couldn't put them on a classical computer because we needed too much memory. And so you could try to actually, I can tell the experimentalist what to put, and they can try to calculate the physical properties. Okay, so I think I'm going to end up there. This is an interesting approach, and I think in part because it sort of gets rid of the spatial structure and focuses on the local data in a very nice way. And besides being a pretty picture, I like this because you can just see this horizon out here. So, in the very long term, maybe we can even eventually see the horizon of a black hole using these methods. Okay, that's kind of the longest possible term. But something that appears to actually be within reach and would actually be a lot easier than simulating the entire, large size system. We could just look at the local properties. We could calculate the masses of fields in an empty de Sitter space, the entropy of the black hole. That might be possible within this framework.
That's where all the errors are.
Yeah, that's right. Okay, thank you for your attention.